Okay, welcome everyone. So this video is going to be the first one for our new unit on energy and kinetics. So today we're going to go ahead and talk about something called thermochemistry. So if we think about thermo as a word, we probably think about the word thermal, meaning heat. So this is another way of thinking about the energy or the heat involved in chemistry. So where does the energy go to? Where does it come from? And that's the topic of today. So the first thing I want to remind you about is the law of conservation of energy. And remember, this tells us that energy is not created or destroyed. It merely changes forms. So sometimes that's from kinetic energy to potential energy, or more commonly in the case of chemistry, it's from chemical energy into something like thermal energy or light energy. So we're going to go ahead and work with some examples of that in this unit. So thermochemistry is the study of how energy is transferred during chemical reactions and phase changes. And the important thing to keep in mind is that almost every chemical reaction involves a change in energy. This is because chemicals are lazy, just like we are. If they have an opportunity to go to a lower energy state, they will. And this is when we have reactions that occur spontaneously versus unspontaneous or non-spontaneous reactions that don't follow this trend of going to lower energy. And sometimes we need to help those along a bit. And chemical reactions usually either absorb or release energy as heat, although we sometimes do see other forms of energy such as light. We'll have an example of that today. So a few things I want to go ahead and define in terms of chemistry definitions. So temperature is a measure of the average kinetic energy of the particles in a sample of matter. And we've already talked about this. Things that are at higher temperature have that higher average kinetic energy. If you think about that Boltzmann distribution, it's shifted further to the right, versus things at lower kinetic energy will be shifted further to the left and have lower temperature. So the key idea here is the greater the kinetic energy of the particles, the hotter it feels because it can transfer more of that energy to us. So we're just going to be doing some chemistry conversions with temperature just like we did with gas laws. So I want to use Celsius and Kelvin. And remember, we convert from one to the other using that magical number 273. And technically it's 273.15, but again, we want to simplify a little bit, so 273 is good enough for us. So down below, I have a table of the common values for Celsius and Kelvin in melting point and freezing point, room temperature, and boiling and condensation point for water. So I want you to go ahead, pause this video for a few seconds, literally go ahead, hit pause, and then figure out what those values should be, try and fill them in, and then you'll get a chance to check them. So pause the video now. Okay, so here are the answers. So remember, in Celsius, the melting or freezing point of water occurs at 0 degrees Celsius. In Kelvin, we add that 273. Room temperature, if it's 298 in Kelvin, it's going to be about 25 minus at 273 to get the 25. And then for the boiling and condensation point of water, it's 100 and 373 Kelvin. Go over is the term heat. So heat is the amount of energy that's transferred between samples due to differences in their temperature or differences in their average kinetic energies. And a key idea here is energy always flows from hot to cold, never, ever, ever from cold to hot. And heat is usually measured in the unit of joules, okay? It's pronounced joules, just like a diamond or a ruby. And this is the SI unit of energy. We have different types of reactions. One type of reaction we can have is an exothermic reaction. This is a reaction or process that releases energy. So I always remember exo, exit, it's exiting. So in this case, energy is a product of exothermic reactions. We're listed after the arrow on the right-hand side. An example of an exothermic reaction is making bonds. Okay? Chemicals want to form those bonds because it lets them get to a lower energy state and they get rid of their excess by releasing it. We also have the opposite, which is endothermic reactions. So endothermic reactions need to absorb heat from the outside. So I always think endo, enter. Okay, so in endothermic reactions, energy is a reactant. So the reaction will not occur unless energy is being added to it. So in this case, bond breaking is an endothermic reaction. Okay, because the chemicals don't want to break those bonds because it lets them be a lower energy state. So we have to put energy in order to break them. Okay, so let's go ahead and talk about some examples. Now, I know for these examples, you have something that kind of looks like a graph on your paper. Just go ahead and leave that alone for right now. We'll come back at the end of the video and talk about those and fill those in. So the first example I want to talk about is glow sticks. So remember with the glow sticks, you go ahead and you crack them, you break the little glass tube inside, and when you do that, you shake it up, and that allows the chemicals to mix, and then we are creating light. So for the idea of glow sticks, I want you to go ahead and answer the questions. Is this reaction exothermic or endothermic? And then with this equation in your notes, I want you to add the term energy either to the reactions or the product side. So think about which side it should go on. So go ahead, pause your video for a few seconds, answer those two questions, and then we're going to go ahead and talk about the answers. So go ahead and pause it now. Okay, so if we think about this reaction, we are releasing light. So because light is exiting, this is going to be an exothermic reaction. Because it's an exothermic reaction, our energy needs to be on the product side. So it needs to be on the right-hand side. And remember, the order that you list the products doesn't matter. I have CO2 and then the dye and then the energy. Energy could come first in that list. It just needs to be after the arrow. Good, so let's go ahead and talk about the next example. An instant ice pack. So sometimes you get these if you go to the nurse or the athletic trainer, or if you have an emergency, can you open up? Sometimes you see them in there. So in the instant ice pack, you have a container of ammonium nitrate, which is kind of like an ionic compound. It has little white beads in it. And inside of there is little plastic bags. So you need to go ahead and squeeze your instant ice pack. That breaks the water container that it's in, but still leaves it inside the overall ice pack. Those two things mix together, and then they start to get cold. So for the idea of the instant ice pack, go ahead and answer these questions. Is the reaction exothermic or endothermic? Add energy to the correct side. What type of reaction is this? So is this combustion or synthesis or decomposition or a type of replacement reaction? And then in this reaction, where does the heat flow from and where does the heat flow to? So go ahead, pause the video and answer these questions, and we'll talk about it in a few seconds. Okay, so if we think about this reaction, our ice pack is getting cold. So this might be a little bit counterintuitive because in order for our reaction to get cold, we have to actually put energy into our reaction. That's because it's stealing heat from its surroundings and it's putting them into chemical bonds. So because of this, the ice pack is an example of an endothermic reaction. Okay, so we are pulling heat from the surroundings to form those bonds. Because we pull it from the surroundings, our hands or the air, that's why it feels cold. So because we are adding in that energy, we're pulling it from the surroundings, energy needs to be on the reactant side for the reaction. And if we go ahead and think about the reaction type, this is going to be a double displacement reaction. So think about the OH as going to the ammonium, and then the hydrogen cation going to the nitrate. And if we think about this, heat flows from the surroundings, so your hand, the air around it, the table, whatever your ice pack is on, to the ice pack itself. Okay, so it's going from the surroundings to the ice pack. That is why it is endothermic. Okay, so our final example we're going to talk about is hand warmers. Okay, so you probably use these on cold days, although we didn't have too many of them this past year. But these are the ones that are sealed in a container. You tear them apart, have your little fabric container of your hand warmers. You go ahead and shake them up, and they get nice and warm to help keep you comfortable when it's really cold outside. So again, for these, go ahead and answer these questions and pause it so that you can have time to answer them yourself. So is this reaction exothermic or endothermic? Write the chemical equation for solid iron undergoing a synthesis reaction with oxygen gas, don't forget about diatomics, to yield iron 3 oxide, and then balance that equation. Add energy term to the appropriate side of that equation, and then think about where heat is flowing from and where heat is flowing to. So go ahead, pause the video again, and we'll check answers in a few seconds. Okay, so this is pretty much the exact opposite of our last example. So in this case, we are releasing heat. It's coming from the chemical bonds out into the environment, which is why we love them on cold winter days. So this is going to be an exothermic reaction. we go ahead and write the balanced chemical equation, it's going to be 4 iron atoms plus 3 oxygen molecules gives us 2 molecules of iron 3 oxide. Now, I could go ahead and add those phase labels in there. I'm told that iron is a solid, oxygen is a gas. And if we think about this, the stuff that's left over once your hand warmer finally cools down and it's released all of its energy, that is going to be a solid, so we could add those labels in as well, but you don't need to in this case. So we go ahead and think about this. Energy is being released, so it's going to be on the product side. And then for this reaction, heat flows from the hand warmer into our hands or to whatever else we're trying to warm up. Okay, so that is a great way to kind of compare the different examples, but sometimes we want a way to compare graphs or to compare trends over time. And the way we can do that is using something called reaction coordinates. So reaction coordinates show the change in energy during a reaction. In this case, reactions, what we start with are always on the left, and the products, things we end with, are always on the right. And in the middle is something called the activation energy. It's kind of like the bump on a camel. It's what we have to get over, how much energy we need to put into a reaction to get it going. So sometimes we have to heat reactions up really high. Sometimes we need a spark. What do we have to do to actually get that reaction to go? So we have 2 different reaction coordinates, one for exothermic and one for endothermic. So in endothermic reactions, that's what we're seeing here, the energy of the reactants is lower than that of the product. So we start low, we have our big bump in the middle, a big hill, and then we end up high. That's because we're taking energy from the surroundings and it's now in our material. The opposite of that is exothermic. So in this case, we have a higher value for our reactants and a lower value for the products. That's because we're getting rid of the energy. So we're going from a high energy state to a low energy state. And in both cases, we still have that hill, that bump in the middle, that activation energy or that activation barrier. So I want you to go back now and fill in the pictures for each of these examples. Which should it be? So go ahead, take a few seconds, draw your pictures out, and then we're going to go over the answers. So go ahead, pause the video. Okay, so let's go through these examples. For the glow stick, okay, remember that is releasing light. Because it's releasing light, it's exothermic. So we start from a high energy state with our reactants and we go to a low energy state for our products. The next one is our instant ice pack. So we are absorbing heat from the surroundings. That's why it gets nice and cold, because it's taking heat away from you. So it goes from a low energy state to a higher energy state. That's what our endothermic reaction looks like. And then finally, example 3, our hand warmer. Again, we are taking a high energy state and releasing it to your surroundings. So that's exothermic. So that's what your graph should look like for there. So if you have any questions, go ahead, write them down. Come see me during virtual office hours and we can talk them over. Otherwise, feel free to send me a message on Remind or to send me an email and I'll be happy to help you guys out. Thanks for watching and have a great day.